Welcome to Yaka Digital Network videos. If you stand next to a burning charcoal sagiri, you feel the heat instantly radiating outward. But if you mix urea fertilizer into a jerry can of water, the container actually turns cold in your hands. These everyday tasks perfectly demonstrate the flow of chemical energy. Chemists track that energy flow using standard enthalpy change, or delta H. It measures the heat absorbed or released by a reaction at constant pressure. To compare different reactions accurately, we measure them under strict standard conditions, 1 atmosphere of pressure and exactly 298 Kelvin. This diagram shows the energy pathway of a reaction. Before molecules can transform into new products, they have to climb this initial energy hill. That peak is the activation energy. It's the minimum spark required to break the initial chemical bonds and get the reaction started. Once over that hill, the reaction finishes in one of two ways. If the products rest at a lower energy state than the reactants, the leftover energy is released as heat. That's an exothermic reaction, giving us a negative delta H. If the products sit higher, the reaction absorbed heat from its surroundings, making it endothermic with a positive delta H. Mapping this energy profile lets us predict whether a chemical process will release useful energy on its own, or if it will require a constant power source just to keep going. When we write standard thermochemical equations, whether for formation, combustion, or atomization, the physical state of the chemicals dictates the energy values. A gas has vastly different internal energy than a solid. If you neglect these state symbols, your equation is thermodynamically invalid. Calculating those exact energy values relies on Hess's law. Think of it like traveling. If you drive directly from Kampala to Jinja, your total displacement is exactly the same as if you took a detour from Kampala through Mukono and then drove to Jinja. The start and end points dictate the total journey, regardless of the route. Molecules follow that exact same logic. The total enthalpy change to go directly from reactant A to product B is identical to the sum of the enthalpy changes if reactant A first turns into an intermediate C and then reacts to form product B. There is a strict mathematical rule here. If you need to reverse the direction of an equation to complete your cycle, you must algebraically reverse the sign of its delta H. An endothermic step forward becomes an exothermic step backward. This allows chemists to calculate the exact energy released by highly explosive or physically impossible reactions safely on paper, without ever having to risk performing them in a laboratory. The ultimate test of Hess's law is the Born-Haber cycle. We use this method to break down the formation of massive, three-dimensional ionic lattices, like sodium chloride, into individual calculable steps. This diagram illustrates the energy required to prepare the ions. We map the energy-absorbing upward steps first. We account for the atomization of the elements into gases, the ionization energy to remove electrons, and the electron affinity. Then we map the energy-releasing downward steps. The gaseous ions condense into the crystal, releasing lattice energy, and the cycle closes with the overall standard enthalpy of formation, bringing us back to the solid lattice baseline. Now it's your turn. Pause the video and use this data table to construct a Born-Haber cycle for magnesium oxide. Be careful. Magnesium forms a 2+ ion and oxygen a 2- ion, so you must include both their second ionization energies and second electron affinities. Let's check your work. Notice the oxygen calculation. Because we are forming 1 mole of MgO, we only need half a mole of oxygen gas. That means you must multiply the atomization energy of oxygen gas by exactly 1/2 to balance the stoichiometry. These specific energy accounting cycles prove why compounds like magnesium oxide form incredibly stable crystals, while other theoretically possible ionic combinations instantly fall apart. We can apply lattice energy to the real world by examining how salts dissolve in water. The total enthalpy of solution depends on breaking the solid lattice into gaseous ions, and then hydrating those ions in the solvent. A salt's ability to dissolve is a direct thermodynamic tug-of-war. The system must overcome the endothermic energy required to shatter the lattice, using the exothermic energy released when water molecules surround and hydrate the individual ions. To master thermochemistry, follow these 4 cardinal rules. Always check your positive and negative signs. Always include physical state symbols. Always multiply your energy values by the molar coefficients. And if you reverse a reaction arrow, you must reverse the enthalpy sign. You can watch more videos for all classes here and get all content at www.yaka.cc.